Hi, I'm Gabriele Berton, and I'm going to introduce EarthLoc, a method for localizing astronaut photography by indexing Earth from space. In this paper, we define the task of astronaut photography localization, offering a retrieval approach to determine the location of photos taken by astronauts. An astronaut photo is a picture of Earth taken by a human in space, and as of today, we have more than 4 million of them. Astronauts undergo photography training to take pictures that are used for scientific research and disaster management. For example, they take photos of floods, wildfires, hurricanes, and volcanic eruptions. The big problem is that these photos need to be manually localized in order to be useful. The value added by having a human in the loop to take a photo also makes localizing a photo extremely difficult. From the International Space Station, astronauts can see an area of 20 million square kilometers, about the size of North America. The photos can cover an area of just 0.0005% of the visible area, so finding an astronaut photo is similar to finding a needle in a haystack, and it can take hours. Despite being so difficult, these images are so important that already 300,000 of them have been manually localized. In the words of NASA Earth Observatory, this is a monumentally important but monumentally time-consuming job. To solve this needle in a haystack problem, we take an image retrieval-based approach. We select tiles from Earth and train a retrieval model to understand which tiles, and therefore which Earth locations, are most similar to a given astronaut photo. We call this image retrieval model EarthLoc. We use satellite images to build our database, which we also use as training set. Astronaut photos can be almost anywhere on Earth, can have any orientation, and can be at different scales. And so we sample images at 3 spatial resolutions, 4 rotation angles, and 4 years. This produces a total database of 700,000 images. To train EarthLoc, we sample images from regions, so that from each region, like this deserty-looking region here, we sample 4 different images from the 4 different years. We then use a multi-similarity loss to pull together these images in feature space while pushing faraway images from different regions. As you can see, this is a trivial task and the loss quickly goes to 0. So to make it more complicated, we use cluster batches, so that within each batch, all the images are taken from similar looking regions. For example, within this batch, all the images are sampled from plains. From the next batch, they might be sampled from deserts or coastlines and so on. And these improve results by 4.4%. To make the task even more complex for our model, we use a year-wise data augmentation, so that to images from a given year, we apply the same type of data augmentation. Images from the same year will always be from different regions. And so this makes the task even more complex for the model. And it makes sure that it's going to be robust to this type of data augmentation. This also improves the model by 4.3%. And finally, we use a neutral-aware multisimilarity loss. So a multisimilarity loss assumes images to be either positive or negatives. But we can see, for example, between this green region and this big gray region, there is only a small overlap. So we do not want to consider these two regions as positives or neither negatives. And so we consider them as neutral and we don't count them for the loss. Here are some qualitative results. In each quadruplet, you can see on the top, on the left, the query and the top 3 candidates produced by retrieval. You can see that typically there is more than one rotation of the same region in the top 3 candidates. Like you can see here, these 3 images are from the same region, just rotated, which means that EarthLoc learns some rotation invariance. Also, we can see that most incorrect predictions are of visually similar regions. And here are some quantitative results. We can see the EarthLoc achieves state-of-the-art while being 50 times faster and producing 10 times smaller features than the second best model. Finally, because we introduced such a new task, we point out that there are so many possible future works and extension to this paper, and we welcome future researchers to help us to work on this task. So to summarize, we defined the task of astronaut photography localization. We created a new dataset, and we proposed a new method called EarthLoc. Code and data is publicly available, and thank you for your attention.